So you get solution 1, solution 2, so on. Now you patch these all up to the final solution. Okay, so this is the divide and conquer paradigm that we saw last time. The conquer step is hidden. You know it's there, right? Alright. So this is what we saw. And then we also saw how you do solve recurrences. Okay. So we said that if you have a divide and conquer algorithm, then typically what you do is you figure out how much time is spent in the conquer step. Okay, so that's the additive term. Or sometimes you need to spend also some time in the divide step. Okay, so that's called the work that you do at this stage of the algorithm. And we write down a recurrence for its running time. Okay, and this is what we said last time. And we saw the example of merge sort, where we said that if you, here we define P of n to be the time to sort an array of size n. Okay. So n size n. Okay, so that's P of n. Then we wrote down a recurrence which basically said P of n is 2 times P of n by 2 plus n. Okay. Last time we saw how to solve things of this kind. We drew this recurrence tree and stuff, and we said that this ends up solving to n log n to the bit. Okay, so I don't even think there was any constant here if t of 1 was equal to 1. So I said that there's two things you've got to pay attention to: what the base case is and what this additional work step is. And we have to add up additional works on each level. Okay, so this is how we solve recurrences. Okay, and then so this was a case problem for which it was kind of easy to see a divide and conquer algorithm. Okay, and then we looked at multiplication. Okay, so integer multiplication. Okay, so here you have two n-digit numbers. Okay, so it's important that the number of digits is n. So the numbers are like exponential in n, right? So there's something like 10 to the n. And we saw what is called this Karatsuba's algorithm. Okay, so if you have two n-digit numbers a and b, this length is n. We said that you break a up into two pieces, break b up into two pieces, and you solve using this trick. Okay, so if you have so you can write a as that, b as that expression, and a times b we said is this expression. If you want to do it naively, then you need 4 products of n by 2 digit numbers, right? So you've got to compute xu, xv, yu, and yv. Then we said you can do this in a slightly better way. So you observe that we don't literally need xv and yu, we just need their sum. And this was the main observation, that that we only need the sum x v plus y. And this you can do by first doing a multiplication x plus y times u plus v, and then you subtract off 2 of the things that you had to compute anyway. Okay, so you had to compute xv and yv and xu anyway. So you subtract those out, and this is what you get. Okay, so if you've done homework 0, then you would have seen like this kind of like the squaring, multiplying problem that I give there. Okay, so that's similar sort of a trick. Yeah. Good. So what we said is that then you get a slightly better recurrence. So you get T of n equals 3 times T of n over 2 plus some constant times n. Okay, so where does the constant times n come from? Yeah, summing various things, subtracting stuff and so on. Right? Okay, and then we said that you can solve this recurrence as follows. You observe that T of n is 3 times T of n by 2 plus some constant times n. You write it down. Then you basically get, so you essentially get 3 to the k times T of n by 2 to the k. So every time the n part goes down by a factor of 2, but then you get a 3 as the multiplier. Okay, so that's why this is a little bit superlinear. So you get essentially this, plus it turns out the other terms are actually smaller order. But typically you've got to be careful. Sometimes this term dominates and sometimes other terms dominate. In this case it turns out that this term dominates. Okay, so you get this, and we are interested in a k where k is such that n by 2 to the k is 1. Okay, so k is log n base 2. In which case this expression becomes 3 to the log n base 2 plus some lower order. Okay, because again t of 1 is 1. That's what it is. Okay, so this is what you have, and these are lower order terms. And what is this expression? We said that this you could write it as, there were some questions about it after class, so I just thought I would spell it out now. Sorry? Yeah, so in general, a to the x, you can write it as 2 to the x log a. Okay, so this is just manipulation, so that now you get, so you could write this as 2 to the log 3 base 2 times log n base 2. Okay. Now you observe that 2 to the log n base 2 is actually n. Okay. So, I mean, in fact, like if you have some number z to the log n base z, this is n. This is again basic logarithms. So this part comes to n. And so you just have n to the log 3 to the base. Okay, so this is the same as this. You can see it in many ways, but this is one way of seeing it. Okay. Yeah, so this is what gives this running time, and this number turns out to be 1.57. Okay, question? Yeah.
You said that the first term is dominate the sum.
Yes, yes.
But after the first term, we have a chain log n minus 1
Yeah.
of terms.
Yes.
The
Yes,
sum-
to be formal, you've got to actually show by induction that, yeah, you have to actually have a bound.
I cannot say what we said for all problems.
No,
I mean,
no,
the first
yeah.
one dominate.
Yeah, so it's just, I said it here because, I mean, I want you guys to go and verify this, but yeah, to be correct, you have to actually literally sum this, but this is not very difficult to sum if you assume something inductive. Yeah, so very often what you do is you do some heuristic calculation where you say that, at least this is how I prefer you guys think about these things. When you're solving recurrences, no recurrence is really difficult. Okay, so people say solving a recurrence is like fighting a 6-year-old, right? So initially they could be a bit annoying and stuff, but eventually you'll be able to solve it. Okay, so that's kind of the way it is. So what you do is you think about it a little bit, you use some heuristic, maybe you guess that the first term dominates, then you come up with a guess of what the answer could be, and then you just prove it by induction. Okay? So if someone were to tell you this thing, that the answer is some constant times this, then it's very easy, right? Then you go ahead and plug it back there. Okay? And then you say that, sorry?
It works for T1. And
yeah, it works for T1.
And n plus 1.
So you don't have to, you can't do n and n plus 1 because it's n by 2, right?
Okay.
So you just assume it holds until n and you prove it for n. Okay? If you assume that it holds for until n minus 1, prove it for n. And that you can do from it.
I plug the result into the...
Yeah, plug answer should be and then prove it by induction. Okay, so that's the easiest way that works for most problems. So, yeah. Right. So in this case, I haven't explained why you can do this, but yeah. So it turns out you can, but as I was saying, so you could just guess that maybe I can ignore, and then you can end up with this expression. Now you can plug this back into the original recurrence and see that it satisfies. Okay. So what I'm saying is, you do some heuristic to come up with a guess for an upper bound on T. Okay. In this case, the heuristic I've done is ignore a lot of the last few terms. Okay. And I'm saying that, yeah, so then I want to show formally that this is an upper bound on T of n. Right? This I will do by induction. Okay, so I will say that so you will say that we will show by induction that T of n is less than or equal to some constant A times n to the, okay. So this is how you will write such a proof. Okay, so you will guess this by ignoring the last few terms, let's say, and then you say I'm going to prove by induction that this is true for some constant A. Okay, this constant should better depend on that C, right, intuitively. Yeah.
Okay, there is another equation that is smaller than the A times n to the log, and it is still bigger or equal than the T.
Yes, so you could have started with, for instance, n squared, and you would still be able to prove these things, right? So that's why you've got to come up with the best possible guess you can. Yeah, that's true.
So you should prove that this is the minimum upper bound.
So it depends on what you want. Okay, so if you want a really tight bound, yes, we have to show a lower bound also. Okay. But in this case, showing the lower bound is actually easy, because you know that this is one of the terms. This term itself grows like that, right? That's how we came up with this guess. But there are problems for which literally getting the lower bound could be very difficult. Okay, so in this case it's easy. Do you see in this case why it was? Because in our expansion we had this term. This is just one of the terms. So I could say this is bigger than or equal to 3 to the k times t of n by 2. So that gives a lower bound. Right here. All you are saying is that for all n large enough, f of n is less than or equal to c times g of n. Okay, for some absolute constant g. Okay, for some constant c that does not depend on n. Okay, so that's what this means. So I could say that n is O of n squared, right? And this is a perfectly true statement. So this is an aside. And now you can say I have shown by induction that this is true, and you can plug this into the original expression. And you will be able to show this when you pick A equals some 2C or something. So maybe to be safe, you can put like 4C. Yeah.
Shouldn't it be like small O of n square, because that's not a tighter boundary?
If you want, you could write small o. Yeah. So small o. Okay. So this again. Then let me do small o also. So when you say f of n is small o of g of n, then all this means is that for all n large enough,
N is less than.
or rather I should say that for all constants, okay, so for all constants epsilon which are bigger than 0, okay, so if you look at n large enough, then f of n is less than epsilon times g of n. So this happens to be true for n and n squared. Okay, so in this case you could have written that, but yeah, so we don't. I mean, you could also write this. This is fine too. This is logically correct. That's all I was saying. Yeah.
So regarding the induction proof, how would we go about it? Can you just briefly outline?
Yeah. So let's say I want to prove this statement by induction, right? So I assume this is true for all. Assume that this one is. For integers less than n. Okay, and now you say that okay, n by 2 is an integer that's less than n. Okay, so I can assume that that this condition holds for n over 2. Okay, so I'm going to erase this space. Okay. Assume one holds for integers less than n. And then you say that, right, so now I can bound t of n as 3 times t of n by 2 I know is smaller than or equal to this, right? So it implies that t of n is less than or equal to 3 a n by 2 to the okay. And this one is 3a divided by 2 to the log 3 base 2 times this exponent we want. Okay. So yeah. So 2 to the log 3 base 2 cancels perfectly with 3. Okay, so that's what we want. So yeah, so as we are proving this, you realize that this is not going to work out exactly as we want, because there's a small extra term. So, but these things you can always fix. You can say that this is left. You have an inductive statement that goes a little bit off. Okay, so you allow a little bit of slack in this. Okay, so you say that plus I want to find some b so that this is actually less than b times n plus bn. Now you plug that in. Okay, so So you get 3 times a plus this plus b times n by 2. This is now your inductive statement. This is what you are now trying to prove. So this is what you get. And now things are in much better shape, right? So now you have this term, which looks like what you want, okay, plus this 3b to n plus c. So is this good enough? Okay, so this doesn't seem good enough, right? So it's like this part cancels out, this part works out fine. Now this is,
We already have n to the power of 3 base 2, so we can, like, why do we need to consider n anymore? Like, can we not be done?
oh, so this is just to make the induction part work out.
Yeah, so like
So-
after this stage, we can like conclude, right? Because the first part is n to the power 1.5 and the next
No, but you don't want a bigger constant every time. Okay, so that's part of what you should be careful about. Okay, so that's why I'm trying to write down the exact inductive statement. But this is a good exercise for you because this is how one would go about doing this. Okay, so first you come up with an inductive statement, try to prove it, you realize it doesn't quite work out, you need some extra correction terms. Then you've got to figure out what that correction term should be. Okay, and now I've realized that if I have an n as a correction term, this might not end up working out because there's no way I can show that this is less than or equal to b times n, right? And so I'm going to do something a bit more clever here. So let's see what I should do. Just leaving if I made any mistake.
Can't we take it minus 2c? 2c.
Yeah, so that's what I was trying to say. Maybe we've got to do minus bn, and then things might actually work
Minus
out.
2c.
Right. So this would be this, and b has to be c. That's what you're saying. Yeah, we'll pick b later. Okay, so very often these kind of tricks work. So you get this, I guess, and then yeah. So if I pick b to be equal to
Minus 2c.
2c, okay. So I already have a minus. So if I pick b to be equal to 2c, then this will end up working out. Okay. So yeah, thanks. Okay. So this is how you come up with an inductive statement. Okay, so you start off with a guess, then you try to figure out what makes the inductive statement actually work out. Okay. And that's roughly what you've got to do in these kind of problems. Okay. So sorry, we got sidetracked a little bit, but this is typically what you will end up doing. You'll have a main term, do some corrections so that the calculation works out. So any questions? Yeah.
Over there you described the last one and second term should not have t, right?
Second term should have t, right? Oh.
It's the fraction itself n over 2 to the power of k minus 1.
Yes. There is no.
And a second line is n over 2, not 3, right?
Second line is again n over 2, yes. Clearly shows that I've done this in a hurry. Yes. Yeah.
There's any way to define the adjustment of the function I mean, now we try plus, then we try minus.
Yeah.
There's some rules, there's something that can help us to decide how to adjust the function.
Oh, that you
Yeah,
what you
yeah.
have in the induction?
I mean, how to decide the degree of the adjunction.
Right, so the degree usually is something that you make sure these constants kind of get cancelled out. That's how you usually find the degree. Okay. And this here you observed that you had a 3 and you have a 3 by 2 coming, right? You want that 3 by 2 to cancel with this plus c, so it's good to have a minus. Okay, if this were somehow n by 4 or something, then it's fine. You could have had something positive and it'll work out. Okay. So yeah, so these things you just have to play with them a little bit and you will find what you want. Yeah, so as I said, it will be mostly some algebra that you have to kind of play with for a while and it will end up working out. Alright, so I guess we've spent a fair amount of time on this. So let's go, let me say a little bit about faster algorithms. Okay, so it's natural to ask, if you have two n-digit numbers, then the product is a 2n digit number at most. Now, do you really require time that is something like this, as n to the 1.5 to multiply two n digit numbers? Okay. And it turns out you can do better. So, in fact, in the homework, we do slightly better than this. Okay, so you will end up with a function of n to the 1.45 something. So this is how so this is what we'll see in the homework. But in fact, you can do way better than this also. You can end up doing in time O of n log n. See this? It's not exactly this. It's a little bit off, but okay, this is roughly what it's true. Okay. So, does anyone know how this is done? We won't see this in this class, but it's one of these very famous algorithms that we've come up with. Yeah. Sorry?
2 and 2.
Yeah, so that is what we did in the homework. So this will end up pushing this to something like n to the 1 plus epsilon. Okay, but for any constant epsilon, you can get that. But the n for which you have to get this will be significantly higher. Okay, so there is this trade-off. Right, but there's a somewhat simpler algorithm which gets n log n. It's simpler, but it's also more magical. Okay, so this is called fast Fourier transform. Okay, so you would have heard of Fourier transform in physics and stuff. Very surprisingly, you can do it for multiplying numbers also. Okay. And that's, if you think about numbers as polynomials, then this becomes more natural. Right? So polynomials, people use Fourier transforms to manipulate. But yeah, so that's. Okay, so it's a very surprising thing the first time you see this. Why are Fourier transforms used in multiplying numbers? But these are the best algorithms people use. Okay, so you could also ask, what about O of n? And that's a big open problem. Okay, so we don't know that. We know. I mean, it's a natural question because you can add two numbers in time O of n. Can you multiply numbers in O of n? We don't know. So that's a big open problem, we say. So, questions, comments? Yeah.
In the previous problem, why did we assume A equal to 4C?
Minus 4. Okay. Yeah. So, A is what? So, as I stated it, the A wasn't terribly important. A just comes from the base case. Okay. So this is again common. So you have to show the base case for the induction, right? So the inductive steps works out for any A, right? So, but you'll have to show this in the base case when n is 1 or something. Then you'll have to show that A minus 2C is equal to 1. You have to pick things so that this is true. Okay, and this will mean that A is 2C. So any other comments? Yeah, so one of the things that many of you have been asking about in the homework, I have a homework in which you have something like T of n is T of n minus 1 plus T of n minus 2 and so on. Maybe I have T of n minus 3 as well. Right, I have this because if not, most of you will recognize this as Fibonacci. So you know the answer for this. So yeah, so these kind of recurrences, they are called linear recurrences. And these things turn out to have, the answer is exponential in n. Okay. And yeah, so there's a chapter in the book that I point out to in the homework where they talk exactly about these linear recurrences. So you should read, generally that chapter is written quite well. Alright, so before we end divide and conquer, so there's another example which we didn't go to here, but we will see when we do a randomized algorithm. Okay, so that's this example of order finding. Okay, so this again, many of you would have seen this. It's like one of these very common interview questions. Okay, so you have an unsorted array. You want to find the kth smallest element. If it's sorted, it's trivial. If it's unsorted, how efficiently can you do it? Right, so what's the answer for this? Sorry? But heap takes a while to construct, right? It takes n log n to construct. You can do it using binary search trees also, they have the same problem. So, yeah, so okay. If n log n is fine, then yes, you can do heap. The question is, can you do it in just linear time? Yeah.
I mean, you can just, I might be confused, you can just check them each individually and you can't beat that because otherwise you're not looking at every element.
No, but you want the kth smallest. K is pretty
Oh,
big.
sorry.
Yeah, k could be like n by 2 or something. Actually, how many of you have not seen this? If there's a decent chunk, then I'm going to write up a short description of how this works. So that, because it's important that all of you know this. Okay, so this is one of these very cute, very basic facts that you can do this in just linear time. You don't have to sort to find the kth smallest.
May I pick up randomly an element?
Yeah, so that you will see later in the course. Okay, so actually one hint is, suppose you could find, suppose somebody told you what the n by 2th element is. Okay, yeah.
So we can divide the problem set into whatever is the number that we are trying to look at. If it is the second smallest, then we can divide it into 2 subproblems, third smallest 3 subproblems.
Okay.
And then we can pick the smallest.
But why should that be the? I mean, it depends on how you partition, right? Unless you partition carefully, okay. So it turns out divide and conquer is the way to go for this, but you have to divide carefully. Okay. So suppose somebody told you that the n by 2th smallest element, or let's say the n by 3rd smallest element is a certain number. Okay. Then you can reduce the size of the problem by a factor of 2/3. Does anyone see that? So my game is, so this is just to pique your curiosity. Okay? So suppose somebody told you, suppose some oracle said n by 3rd smallest element is x. Okay, it actually literally gave its value. Okay, so then could you construct a strictly smaller instance of this problem? Like my goal is to find the kth smallest, right? So suppose k is something less than n by 3. What would you do?
Is it supposed to be k?
Sorry?
Is that supposed to be a k rather than an n there?
Oh no. So this is just n. That's important. Yeah. So what I'm saying is, somebody tells you that okay, I won't sort this array for you, but imagine there was a sorted array. I give you some element that's not at one of these extremes in the sorted array. Okay. Then I claim that you can reduce the problem size by a pretty decent amount. So, any guess?
So if the element is already known
Yeah.
to us, then rather than then it becomes simple. We just have to, like you said, 2/3 time we can find this element if we divide it into 3 parts.
No, but this is already given to us, right? So how are you? So the question is what he was kind of getting at. Like, suppose somebody gave you the n/3 element. How does it help you find? How could it help you find the kth smallest? Where k is something that
Is
maybe you haven't spoke. Yeah.
Just curious, would you create a new subarray with everything smaller than, so now you have a
that will take
What you would do is, it's exactly what he said. Basically, you know this one element. Okay? So I'm going to go through the original array. I'm going to put everything that's smaller than this x. I'm going to I'll create one array out of this, and I'm going to put everything bigger than x. I'll create a bigger subarray.
quick sort. Something like quick sort.
Something like quicksort, yes. And now you say, oh, okay, I know that there's roughly n by 3 elements here, there's roughly 2n by 3 elements. Now if your k was smaller than n by 3, then do you know where to look for now? Where to look? Okay, so you have to look here, right? If your k was smaller than n by 3, you know that your answer lies here. So your problem size dropped to from n to n by 3. And if k was bigger, you know you have to look here. Okay? So this is kind of the idea in these things, that you've got to look at basically you take n time and you drop the problem size by a constant factor. Okay? So you'll get a recurrence of form t of n equals n plus t of 2n by 3. And this one you guys can solve it without looking at, without literally doing induction. Anybody say how you do it? This one is particularly easy, right? If you do the plug and chug method. So basically you just keep expanding. So you say that t of n is n plus t of 2n by 3. That's 2n by 3 plus t of 4n by 9. So it's n plus 2n by 3 plus 4n by 9 plus 1. Okay, and this is a geometric series where it's 2/3 to the power of k, and this one adds up to a constant. I think it's 2 maybe. Okay, so that's, I think it's 3. Okay, so this is 3n. So this is how you solve this recurrence, and this is just O of n. Okay, so if you could somehow do n amount of work and reduce your problem size to a constant smaller, then you are kind of done. Okay, and that's the idea behind this thing. Now the question is, who will tell you the oracle? Who will tell you the n by 3rd element? This is not so hard, it turns out. One idea is what he said. Is you pick a random element. It's not going to be the n over 3rd, but it's not going to be at the corners, right? It's going to be the decent probability. It's kind of in the middle. Okay? So that's one idea. And you can also, there's another deterministic way of doing it, which I will write some notes on it. Okay, so this is something you should all know, because it's one of these few surprising things that you can do in linear time. Okay, so a priori one would think, if you want the kth smallest, how can I do it without sorting? Okay, but the point is you don't need the whole sorted array, you just need the kth smallest. Yeah.
So here the value of k is greater than n by 3 or less than n by 3?
I don't care. So if it's greater, I will look in the right side array, and I won't look for the n by 3rd array. Right? I will look for whatever 2n by 3 minus k. Yeah.
You could do this other way, right? You could maintain a subset, k smallest elements of A, and then.
But how do you make that?
Okay, first k elements. There's a whole array.
Yes.
you always maintain min and max.
Yeah?
Yeah. And so first k elements you maintain the min and max, and then next element comes. So if something if this is greater, this won't enter into that. If this is out of the bound, this won't enter into the array. So that way you always maintain the k array, and then towards the end users.
How do you update this? How do you update this k array?
That's what I said. I mean, so you have min and max.
Yes.
So a new element comes,
Yes.
and if this is not inside this range,
But you've got to maintain all of them, right? There's no way you can maintain min and max without maintaining all of them. Because a new element shows up, you throw out the max, but you've got to know what's the second max. That would now become the new max. So you've got to keep the whole thing. And as far as I see, this would take n times k time. Okay, so I might be wrong. We can talk about it later. Yeah. Yeah.
Did I mishear you? Did you say you can pick a good pivot deterministically in constant time?
You can, no, in n time.
Okay.
If you allow randomization with high probability, you can. Yeah. Because what you do is you pick very unlikely that it's at the very corners of it. So
Okay.
that's the idea behind this.
Are we relying on that, or are we using something deterministic for worst case?
There is a deterministic thing which I will point you guys to. So there's a clever deterministic way of finding. So this is, I'll call this element an almost median or something. And you can find an almost median, and then you can break up the problem into significantly smaller. Okay, so I'll point you to how you do this deterministic.
I have a doubt. Do the two partitions, do they have to be sorted? Like, do we have to
No.
find an order?
No, that's the important thing. So you break this problem up, but you only keep things, I mean, because you can't sort it, right? So you've got to, all you know is that these guys, all you know is that this is a smaller array. That's all you use. Okay? Yeah.
How to choose the median number so that we can always visualize into what we are doing?
Right, you cannot. So what you will do is, you will end up finding a number which is not at the extremes. Okay, so you will be able to guarantee that there are n by 4 numbers on smaller than this number and n by 4 numbers larger than this. Okay.
How you calculate the t function because each time you always cancel with each
Right, so what you will be able to do is that you will just be upper bounding this by t of 2n by 3. It will actually be t of something else, but you know that this number is smaller than 2n by 3. You know that t is an increasing function, so you can always upper bound this by.
Then how about t n minus 1? This is greater than 2n over 3.
No, but so that's the thing. So it will not. It will. You will be able to guarantee that it will never be tn minus 1. Okay, so.
Guarantee that.
Oh, I will send you a write-up on how to do this. I don't want to get into this. Yeah. So that's the algorithm, that you can somehow do this cleverly, and you'll be able to guarantee that you're not in the corners. Okay. So yeah. All right. So let's take a very a minute or so break, and then we can. I want to start with dynamic programming. So I kind of assume that most of you have seen this, but it's if you haven't seen this, it's good to actually see this well. Not yet. So I have used it in the very end over here. So you will go down until you actually get I always ask for a bigger notation. What you get is that your manufacturer it's just value at once. So whatever it is, just manage it. Thank you. Yeah. Yeah. I mean, oh, you mean like for different n? It should be parameterized by n. That's also. So what I mean is, the array will be of size n. No, because it makes sense only if it's a constant. But I mean, I can't give you an array of size 10. Right? But if you give me an array of size 10,
Okay, so we will mention this like a way to build an array of variables.
yes, exactly.
Oh,
Yeah. But it's, but you will, that's normally how you describe that. So what does say, take this array. You don't know K exactly. Yeah. That's what we are doing. We are putting everybody less than the point of number into one array, which is bigger than the other array. Checking, yeah, we are sorting with respect to this number. You might just know that this lies between n by 3 and 2. That's also okay because when we are putting these numbers to the lessons, you know exactly how many parameters are yes, with some expectations will be pretty that's right. You only get about the not in the worst case it will take longer. But if you probably
And then you say
oh yeah, I also did that. Yeah, thanks so much. Yeah. Alright, so let's continue. Okay, so today I wanted to start talking a little bit about dynamic programming. Okay, so this is something else that many of you would have seen. Seen some form of it in the past. Okay. So, how the phrase dynamic programming came about. Oh, okay. So what?
So the inventor was studying maths, and the person who was in charge, he really hated maths.
Okay.
So he wanted nothing to do with maths research. But dynamic programming sounded interesting enough. So the inventor thought that, if I just hide my maths research under the guise of dynamic programming, then I would be safe.
Okay, so that's basically right. I mean, so this is this guy called Bellman who came up with this notion. And you should understand that these are all military people who came up with. So many of early algorithms research happened in the military. Okay, so there was this corporation called the RAND Corporation. They were the first guys to study flows. They were modeling troop movements and things as graphs. The first people to also look at a lot of graph algorithms such as flow and so on. Okay, so that's why this Bellman-Ford algorithm is named after Bellman and so forth. Okay, but so he didn't want to use math, as she was saying, so he came up with programming, and then this was programming for moving things, so he called it dynamic programming. Okay, and the name just stuck because it sounds cool. So it has nothing to do with what actually happens. Okay. So, but the way you should understand dynamic programming is that it's kind of recursion, but it's recursion done correctly. Okay, so it's without waste in some sense. Okay, and I'm going to actually pick. So I'm going to put out this document which kind of talks about the history of dynamic programming and some of the early problems people studied. And I'm going to look at one problem. So they motivated in terms of bombing targets, sounded too harsh, so I looked at it like happiness and candy. So let's stick to this version. Okay. So I didn't want to do the usual longest increasing subsequence and so on. I'll point you to links to do stuff, to things like that. Okay, so let's consider this problem. Okay, so you have, let's say, k types of candy, and each one has a happiness for the number of dollars spent. Okay, so let's see a picture. So it's interesting that this is like the first dynamic programming problem people ever studied. So for every type you have a graph like this, which is the amount of dollars you spend buying this and the amount of happiness you get. Okay, and you assume happiness can be measured. Tapers off, maybe it falls down. Okay, and you have, this is for type 1. Then you have the same for the second type of candy and so on. Suppose somebody gives you these plots. Right? So this is 1, this is 2. Okay, and now the problem is you're given a budget of $D. And how much candy of each kind should you buy? So is the problem set up here? So maybe you want to buy the initial portion. So these graphs need not look so nice, right? So these graphs could look, maybe it's like this, maybe then it suddenly went up, then it tapered off. Okay, so diminishing returns is typical, but need not always be called. Okay, so yeah, so how would you solve such a problem? Okay, so how would you recursively solve such a problem? Anyone at the endish? Yeah.
Probably the most except with each of the graphs, you see like for each dollar at every level, achieves the most happiness. So kind of, let's say type 1 is the most happiness for first dollar spent, and type 2 is second dollar, and in a manner to kind of aggregate and get the best combination.
Yeah, so that's very reasonable, right? So you're saying that try $1 for this, and now you have some budget left, you have some amount of happiness left. Try seeing if you should spend more over here, or try seeing if you can get more from spending $1 over here or here, and so on. So that's reasonable. Yeah, any other?
We could sort the candies which give the most happiness, and we take the candy which gives the most happiness first and use it completely, and then this next happiest candy and then use that.
Okay, so let me write down the two approaches. So one approach that we've seen is, one approach that he mentioned is dollar by dollar. And see how much you're doing. The second one is more a greedy approach. Okay, so here, pick the best candy, go all the way until you think that you're not doing very well, stop there, try a new one, and so on. Right? So this is also reasonable.
Even if you take the greedy one, we have to recurse to all possible combinations.
So that's what I was going to get at. So the greedy one, the problem is correctness.
Yeah.
So how would you know that this is the best way of doing things, right? So that's we'll get to that next week when we do greedy algorithms. But this is a good approach to try. Yeah. Oh, that's all you want to know. Okay. Yeah. So yeah.
So we have $D. So first, imagine it as a tree. So in the first instance, we will for type 1 we will have $1 and then remove that dollar from $D and then go to the next level. For type 2 we will subtract.
But in the next level, do you still consider you might want to spend more than $1 on the first tree, right? On the first type.
So in the next branch we can do that. We can do for $2 and the remaining $. But the problem will be that there will be some sub-problems which are already looked at in previous levels.
Okay. Yeah, so this is what we will get at, right? So whoever has seen dynamic programming, this will sound very familiar, right? So this is what we would somehow want to do. But this approach is very similar to this. Okay? So in some sense saying that don't just do dollar by dollar, in some sense try to figure out how much. Is this color okay for people? No? Actually, what about this? This one is still fine. Yeah. So they say that yellow on black is the best contract. Maybe this is not black enough. So this is a variant of this where you say figure out how much of type 1 branch out. And you have another reasonable approach. So, right, so all of these are good approaches. Okay, and the greedy one turns out to have issues of correctness because if you go all the way, then maybe you've got to backtrack, remove it, and so on. Okay, so that we'll see that sometimes it's not so bad if the number of dollars you have is much more than what these curves go up to, then it's actually perfectly fine to do greedy. Okay, so we'll see that those kind of things when you do approximation algorithm. So, I mean, it's not perfectly fine. You won't get the optimum solution, but you won't be far off from the optimum. Okay, so that's. Okay, so today I want to look at kind of these two approaches, right? So in some sense, try to figure out, assign some dollars and then move on to the rest. Okay, so we want to do this, essentially do it as a search tree. Okay, so you have, there are k types of trees. So how does this work? So first you have $D, like balance D, and yeah, so this is what we have. Then you say that okay, I'm going to do this second thing where I once and for all figure out how much of type 1 I will take. Okay, so that I don't have to keep considering type 1 again. Okay, so you could do that, but I mean, this is just easier, right? So since we are anyway building a search tree, you can try to be a little bit efficient. So figure out how much to spend on this. So there will be cases here. And what do the cases correspond to?
Different dollars spent for type 1.
Sorry?
Different dollars spent for type 1.
Yeah, so the amount that you spend on the type 1. Okay? So you say that I buy $1 of type 1. This is like $2 type 1. So maybe there is a maximum, or maybe you go all the way up to D. So okay, and in each case you have a new balance. Okay. And now you've got to figure out, oh, how much do I spend on type 2? Okay, so this is balance D minus 1, this D minus 2, and so on. Okay, so this is a perfectly reasonable way of solving this problem, right? So what's the depth of this tree? It's K, right? Because there's every time it's you have this. So you have depth K. Okay, and this is what we want to essentially do, because every time we have some amount of happiness, and you want to figure out how much we need and so on. Okay, so this is good, but how many nodes are there in this tree?
So that will
Sorry?
for at every level,
Yeah.
if type 1 has, if there are whatever dollars spent on type 1, that many nodes of dollar left, and after that, however many dollars can you spend on type 2.
Okay, well that's true, but is there an absolute? Yeah.
D.
Why is it D?
Because it goes D minus 1, D minus 2 till D is equal to 0. So
You mean the balance?
yeah,
Okay.
for every node. So total will be D.
That's a levels though, right? Not nodes.
No, the levels are K, right? Yeah. So K is the number of types, but I guess are you talking about number of nodes in every level? So that was going to be my next question. Can you say how many nodes are there in every level? I mean, there are technically lots of nodes, right? Because this is an exponential size tree just because, basically, if you went this way, if I wrote it as a tree, this is actually literally going to be exponential. It's going to have size 2 to the k essentially, or a d to the k depending on what this number of choices is.
Candy, and then we change. We can come back to that candy.
Yes.
And we can come back to
You can officially, yes. But the point is that we are not, but do you need to? Or would you have covered it somehow in this tree?
No, it depends the number of nodes. If we can come back, the number of nodes is different. If we cannot.
That's also true. But I mean, if you can come back, the depth is no longer k, because you could have gone back to 1 and you can keep going, right? So the depth could be as big as d, because you have d dollars for spend and so on, right? So, but I'm not considering, but that you can easily rule out. You can say, okay, I'm going to first figure out how much I want to spend on type 1, then figure out how much to spend on type 2 and so on.
Okay.
Right? Because might as well do it. Because there's no, since we are anyway searching, you don't need to come back to it. You might as well commit to how much you're spending. So that's a good point. But right, so this is true. I mean, this tree has size which is exponential in k. And if you have d at every step, it's actually d to the k. But what you observe is that suppose I have a balance equals something like d prime node here, which came from this path. Okay? And I have a balance equals d prime node that came from some other path. Okay? And they're both in the same level. Okay? So then, what are we trying to do at this node? Right? So at this node, let's say this node is at depth 4. So this is at depth 4. That means that you've chosen how much money to spend on 1, 2 and 3. And you're left with a balance of d prime. Okay? So in some sense what we now need to do is how much to buy of 4, 5, 6 up to k. Okay? So the problems you're trying to solve at this node and this node are exactly identical, right? Because you have a balance of d prime, and you want to figure out how much of 4, 5 and 6 to spend. Doesn't matter if you spend so much on type 1, so much of type 2 and so on. Okay, so you could have gotten to this node from different paths. Okay? But in some, I mean, this node from one path, this node from another path. But the point is that the problem you're trying to solve at this depth is actually exactly the same in both of these. Okay? So, and the reason for this is that our cost function is additive. Okay, so the total happiness, I haven't defined what total happiness is. Maybe I should first. So total happiness is happiness from curve 1 plus happiness of curve 2 plus so on, right? So it's the sum of these ones. Is happiness from type 1 plus happiness from type 2 plus. Okay. So if you were to evaluate the cost of this path, it will be a different initial happiness plus the happiness from 4 onwards will be the same for this path and this path. Right? So the best happiness from these two will be the same from either this path or this path. So that's the point I'm trying to make clear. So I see a bunch of people who might look confused. So ask questions, then I'll see what I mean. Yeah.
So at every level, if
Yeah.
we reach from a higher level,
Yes.
for that level, the total maximum happiness is fixed. Is just one value, right?
What do you mean?
So like when I'm at level 3,
Mhm.
I want, after I've already done till level 3, now I want to go to 4, 5, 6, 7. Now for 4, 5, 6, 7, the maximum happiness level is just one value, no matter from whichever path I come from.
The best possible happiness value, yes, it depends on the number of dollars you have at this point. But if it was the same, then yes, that's the point. Yeah, exactly. So that's the point I'm trying to make. Okay, so suppose I have some $5 and I want to spend it on items 4, 5, 6, 7. Then it doesn't matter what I have done with respect to items 1, 2 and 3. Okay, so I could have made different choices. But the best possible solution, if I just need to buy items 4, 5, 6, 7, property that is true when your objective is just a sum of things. Okay, that yeah. So sometimes you might want to say I get happiness only if I buy 4 and 5 together. Okay, then the problem becomes messy. But if it's just a sum of things, then this is kind of the nice structure you have. Okay, that as long as I know what my balance is and I know what to spend it on, there's only one best answer. And this is essentially the main observation in dynamic programming, that you have a lot of nodes in this graph where you're essentially trying to solve the same problem. Okay? And how do you know there are lots of nodes of this kind? Like if you have one depth, how can you bound the number of different problems you would have?
It's D, I think. D minus the number of levels. We have already traversed. So if you have,
So anyone want to explain why it's at most D? I mean, it could be D minus something, but yeah.
I was not saying that it's going to be as something D minus 1 into D minus 2 into D minus K up to D minus K.
And why would you say that?
Because for the first level there are T's, for the second level there are T minus 1, for each T minus 1 you get T minus 2, D minus 2.
Right. So this is one upper bound, right? So this is even an upper bound on the total number of distinct nodes there are here. Okay, that there's D minus 1. Okay, this is a pretty large number. This is something like D minus K at the kth level. Okay. So this is true. This is definitely an upper bound. That is asking, given this observation that if the balances are the same, you are solving the exact same problem.
Yeah.
Can you say that there are essentially some number of different problems?
So at each level it can only be D, because you can either have D dollars or D minus $1 or D minus $1.
Yeah, so the number of possible values for the balance is only D, because I'm not allowed to spend fractional dollars, right? So the number of different values is less than equal to D. Because of this, there's only D different problems in every level. Okay? And so that's the idea behind dynamic programming. Okay, so you kind of notice that a lot of times the subproblem can just be determined by some small number of parameters. Okay, so in this case, you just need to know which level this this node is and what the balance is at this node. Okay, that's it. And the level will tell you what the subproblem is. Like if it's at level 4, it means you've got to pick 4, 5, 6, 7. And the subproblem is basically determined also by the balance. Okay. And yeah, we'll see how you take advantage of this in the next class over time. Yeah. I used to think the class of 12:10, and my TA politely told me that it's only up to 12:05. So just stop.